let's wrap up basic collision detection by talking about the different collision phases. Now, we mentioned that in CCD, or continuous collision detection, we might do an iterative solution, and that was probably going to be pretty expensive. So we might do something like this. First, we'd create a swept convex shape for the dynamic object, and then we might put a bounding sphere around that new convex shape. And just find the outer extents of it and make those the diameter of a sphere. Now, if those bounding spheres overlap, only then would we actually perform the more expensive collision detection between those swept shapes. Perhaps using something called GJK, which we'll talk about next time. Now, if then we see that those swept shapes overlap, only then would we start iterating to find the exact time of that collision. Now, of course, if we had a more simplistic type of geometry, such as AABBs or spheres to begin with, then we could use a slightly simpler algorithm. But it's still a good idea to always start with the cheapest test first, and then try to refine things down only when necessary. So as an optimization, we do our collision in different phases or different levels of granularity, starting from the most rough approximation and then working our way down towards the more expensive, more refined collisions. And the terminology we use for this is to refer to these different passes of the collision as phases. Specifically, you'll hear the phrase broad phase. A broad phase collision test is something that very roughly try to group the objects into things that we're certain do not overlap and separate them before we even begin this process. And then maybe you would have a mid phase, and in the mid phase you've got some kind of coarse approximation of the shapes to see if there's any more chance that they touch, such as bounding spheres. And then you get to finally what we call the narrow phase. And in the narrow phase, that's where you're doing the detailed collision tests between each individual object. Let me give you as an example of a broad phase algorithm, the sweep and prune. Now there are several different broad phase algorithms, and one of them is this very simple approach, which is you'll take and put an AABB around each of your objects. Now, I'm not saying that the narrow phase necessarily must use AABB. Perhaps they'll use something else. But for the sweep and prune broad phase, we'll put an AABB around each object. And now we'll do one more thing, and that is we'll sort the objects in order from left to right. To see how the idea of sorting the objects helps, let's see what we would do if we were going to just skip this broad phase and just test each individual object. Hopefully you will already have noticed that once you've tested object A versus object B, there's no reason to test object B versus object A again because, you already just did that. So that gives us one quick optimization either way. So if I just list these objects, labeling them A through G, and I just want to test every possible combination of collision, this is the list that I'll get. Object A has to be tested against B through G, but then B needs to be tested against C through G, etc., etc. And in the total, if you count these up, you get 21 tests. So let me ask, what is the big O for this algorithm? All right, that is O of n squared. And you may note it's less than n squared, right? That just means that there's a constant, we don't show the constants. The constant is less than 1, but it's still on the order of n squared. So if we use this sweep and prune technique, where we know that the objects are sorted, they're sorted by their left edge from left to right. So when we test object A versus B, we see that on the x-axis there is some potential overlap there. So those objects need to be tested. And then A versus C, let's take a look at these. A versus C, they overlap on the x-axis. And so does A versus D. They overlap on the x-axis. But then when we get to A versus E, we see that the x-axis of those two objects does not overlap. And so therefore, they can be skipped. We do not have to do the narrow phase of that test. And what's more, we don't even need to do the broad phase of A versus F anymore, because we know that F is somewhere to the right of object E, and object E was already rejected. So we can skip A versus F and A versus G altogether and move straight on to object B. So what happens with object B? Object B needs to be compared against object C. And again, on the x-axis, hey, look, they already don't overlap on the x-axis. And that means we can reject B versus D, E, F, and G. Just skip them all together. And we'll keep going through the algorithm, and what we come up with is, in this case, we only had to do 12 tests as compared to the 21 tests we had before. So now you may notice, if you're paying attention, it's still order n squared. This hasn't changed the big O. What it did is reduce the constant. It's way faster. It's 12 tests instead of 21 tests. And yeah, that's a substantial improvement, even though the big O is the same. Once we've passed the broad phase, and perhaps we've passed the mid phase if we have one, we'll get into the narrow phase. Now, in the narrow phase, we talked about sphere versus sphere. We talked about box versus box. And we've done a lot of talking about convex shapes versus other convex shapes. We didn't really say how to do that, but we did say that we could do that. But then there's even more options, such as perhaps like this shape here is a compound shape. It's not itself convex. And so what we did is we split it into 3 separate convex shapes. Or this one is what we call a convex hull, which is just a convex outer shell for a shape that might have interior concave spaces, but we'll just fill those in and make it convex. Or we could even get crazy and do a more complicated solution. Perhaps we'll break it into individual triangles and ask, do any of these triangles intersect any of these other triangles? Now, I mentioned something called the convex hull, and let's talk about that really quick. All that is when I build an outer bounding volume around a shape using strictly convex polygons. For example, this car here has this interior angle right here is a concave angle where the windshield slopes down and then the angle of the hood scoops up and makes a concave shape. Just a little. If we build a convex hull around it, it might look something like this, and we just fill in those little divots that would be left. And that's something we can do very easily. Most art packages just have a boop, make convex button, and they can just drop a convex hull around stuff. And then probably you're going to want to go in. Another thing, just might want to go in and remove some of the extra polygons because you got a lot of polygons in this shape, and maybe you don't need that level of detail in your collision shape.